a little bit more about that constant mu0, the permeability of free space. Remember that mu0 is the permeability of free space, and free space means vacuum or approximately air, and therefore mu is the permeability of a material, and what it is a measure of is how big the magnetic field, or how the magnetic field is going to be modified by the fact that it's in a material rather than being in free space. So, for example, this comes up, for electric fields, the permittivity epsilon and epsilon 0, that came up when we put materials between capacitor plates in order to enhance the capacitance. Well, we can do the same thing with solenoids. We can put materials inside the solenoid in order to enhance the magnetic field. So what we do is we take materials with a higher permeability, and we put them inside the solenoid, and a typical one is just to put an iron bar. You put an iron bar inside a solenoid, and that helps to, the permeability of iron is larger than the permeability of free space, and so permeability of iron is greater than the permeability of free space, and so it enhances the magnetic field inside the solenoid. You say, well, then you might wonder how that's useful if we want to use this as a magnet, because we're talking about the magnetic field inside the solenoid. Well, actually, what that does is it also helps to, basically, the iron bar is now our magnet. The iron bar acts as our magnet, which has been given a magnetic field by the solenoid, and so we can use this as a magnet and as an electromagnet to, like, do whatever you want, pick stuff up with it or whatever. You just stick the whole thing, stick the end of the, there you go, stick the end of the magnet on something, and it's a really strong magnet, right? This is how we make the kind of electromagnets that you're picking up cars with in the junkyard, etc. As far as dealing with the value of the constant when we're simply trying to do basic algebra, I do want to point out that mu0, which is whatever it is when you look it up, is equal to 4 pi times 10 to the minus 7 in MKS units. We mentioned this in class the other day, 1.2 times 10 to the minus 6 in MKS units, whatever those MKS units are. I do also want to mention that Jordan had mentioned that the units were h over m, and I thought she was talking about something else, and I had tried to relate that to something completely different, but she was correct that the units were h over m, where h is called the Henry, which is a unit we haven't dealt with yet, and m is the meter, so it's a Henry per unit meter. That's an MKS. Henry is the MKS unit of inductance, which we haven't discussed yet, but it's the MKS unit of inductance, so it is a Henry per meter. But the units of mu0 also, you can see, must be, if b is equal to mu0 I over 2 pi r, then we solve for mu0 in units. What we're going to get is Tesla times radius, which is a meter, over ampere, a Tesla meter over ampere, which is, it turns out, also a Henry per meter, but we haven't learned the unit Henry yet. In any case, MKS unit of mu0 and MKS units 4 pi times 10 to the minus 7. I want to point out that makes things pretty straightforward when we're calculating the magnetic field of a straight wire, because if mu0 is 4 pi times 10 to the minus 7, notice that mu0 over 2 pi, which comes into the magnetic field of a straight wire, mu0 over 2 pi is 2 times 10 to the minus 7 in MKS units. So it's a number that's very easy to deal with in terms of quick plugins if we're trying to calculate things. So that B of a straight wire is equal to 2 times 10 to the minus 7, then the magnetic field is 2 times 10 to the minus 7, current over radius, where everything's in MKS units, and so that will give us Teslas. So if we have a long straight wire with a current of 1 amp and I want to know what the field is at a distance 1 centimeter, 0.01 meter, then the magnetic field. Again, I haven't put all the units in here because this is the units of mu, which I haven't put in here. And what we get is 2 times 10 to the minus 5th Tesla. So a long straight wire with an amp of current at 1 centimeter away is a relatively small 2 times 10 to the minus 5 Tesla.